In this lecture, I will start by talking about the channel capacity of a system with one antenna at the transmitter and one antenna at the receiver. And we will look at how it's impacted by the transmit power, by the bandwidth, but also about the communication channel and how it affects the capacity. And we will look at different types of antennas that can be utilized in order to improve the capacity, and how different frequency bands play a role here as well. And that will lead us into the concept of having multiple antennas at the transmitter or the receiver, and we will look at three main benefits that can provide us with. Let us start by considering a scenario where we are transmitting from one antenna to another antenna. And we can model this using a discrete memoryless channel, where XL is the signal we are transmitting at time L in discrete time. We are then receiving YL, which is the transmitted signal, multiplied with G, which is describing the channel. And then we have NL, which is the complex Gaussian noise. And L is a discrete index here, 1, 2, 3, 4, and so on. But the number of times we can transmit symbols like this per second is equal to B, and that is also equal to the bandwidth. The signal power that the transmitter is using for XL is called P, measured in watt, and in energy per symbol, that is P divided with the bandwidth B, or the number of symbols per second. And we are using Q to denote that. For this kind of scenario, the channel capacity is in bits per second, the bandwidth B multiplied with log 2 of 1 plus the transmit power P, the absolute value square of the channel response G, and then we are dividing with B, the bandwidth, times N naught. And N naught is a noise power spectral density. So, as you can see, this channel capacity is depending on two things that we can, to some extent, change. The bandwidth of our communication system and the transmit power P, while the communication channel is given to us and also the noise power spectral density is given by nature. The term here within the logarithm is called the SNR, or the signal to noise ratio. And the interesting thing with this one is that it grows with the transmit power and it is decaying as we are increasing the bandwidth. And it appears within a logarithm. And if we are just changing the value of the SNR without actually caring about B here, well, then the logarithmic part here will grow almost linearly with SNR when the SNR is small. And then, since this is a logarithmic function, it starts to saturate as we are increasing the SNR a lot. So this type of behaviors are dictating how the capacity behaves when we are changing the power and the bandwidth. And let's focus on the bandwidth and keeping the power fixed. Here I've selected that P times absolute value square of G divided by N naught have a particular value. And there I'm changing the bandwidth here from something close to 0 Hz up to 100 megahertz. And you see the capacity here in megabits per second. When the bandwidth is small, well, then we are dividing with a small number here, the SNR is large, and therefore the logarithmic part here is almost unaffected by the SNR. However, as we are increasing the bandwidth, we still have a factor in front of the logarithm. So that's why the capacity is growing almost linearly as we are increasing the bandwidth. This is known as the bandwidth limited region because the capacity is increasing very quickly with the bandwidth. So if we should improve something, it's not to add more power, it is to add more bandwidth. And we have high SNR in this case. As we are then increasing the bandwidth, you see that after a while we start to saturate, and we are actually approaching an upper limit of this kind when the bandwidth goes to infinity. So what happens in this case? Well, now we are in the case where the logarithm is almost a linear function. And in that case, if we take away the logarithm here, we get B times this factor here. The two B's are cancelling out, and that's explaining why we get a factor like this. We call this the power limited region because we have a lot of bandwidth and we need to spread out our power over that entire bandwidth, and therefore we get a low SNR. So if we would plot a similar figure with the power here on the horizontal axis, well, when we are in the power limited region, the capacity is growing very quickly with the power instead, but not with the bandwidth. So these are the typical capacity behaviors. But one thing that's very important here is the impact of the channel, and that is something that we have neglected so far. So let's have a look at the channel behaviors. And we start with some basic wave propagation. When we are transmitting from an antenna here, the signals are moving away from it at the speed of light, because these are electromagnetic signals just as the visible light. The signal is spreading out in all directions, and if we assume this is an isotropic antenna that spreads out the signal equally over all directions, well then, when we are looking at a certain distance d from the transmitter, the energy will lie on the surface area of a sphere, and it will be uniformly distributed or isotropically distributed over that sphere. Say that we put a receive antenna with area A on the sphere at a distance d from it. Then to figure out how much energy it's capturing, we should take its area, A, we should divide by 4 pi d square, which is the total surface area of a sphere having a radius of d. And then the received power is that factor multiplied with the transmit power. A typical example of a receive antenna is an isotropic antenna that can receive equally much energy from all directions. Its area is given like this. Lambda is the wavelength, so we take lambda square, we divide by 4 pi. And if we put that into this expression here, we can see that this simplifies like that. We get lambda divided by 4 pi d, and then we square the entire thing. And let's put in some numbers. Lambda is 0.1 meters, which is what we get at 3 GHz frequency, which is a very typical frequency in 5G. Then if we are measuring the signal energy at a 1 meter distance, then it will turn out that this fraction here is only 0.006%, which is minus 42 decibel. And if we are increasing distance to 10 meters, well then due to this square here, we are losing another 100 times of the energy. So we are down to minus 62 decibels, which means that if we are sending out 1 million pieces of energy, we are not even receiving one of them, but barely. So the point is that the signal energy is diffusing very quickly over the propagation environment. So that means that when we are computing our capacity, it's not only the transmit power and the bandwidth we should care about, but also the impact of the communication channel. And in my previous example, I had an omnidirectional transmitter and an omnidirectional receiver, or isotropic transmitter and receiver, which gave us this expression for how we compute in the absolute value square of the channel. There are other types of antennas, namely those that are directive. In that case, our channel gain becomes the same factor, but then multiply with 2 additional things here, GT and GR. GT is the directivity gain of the antenna in the angular direction pointing towards the receiver, and GR is the directivity gain of the receiver in the direction towards the transmitter. Here's an example of a patch antenna that is radiating all of its energy in only one half plane, in this direction here, nothing on the backside, and we can see that there is a different power density at different angular directions here. And the maximum value here is 6 in dB scale, or dBi scale it's called, because this is how much stronger the antenna is in that direction compared to this type of isotropic antennas. So in this direction we get 6 dBi, or 4 times more signal energy focused in that direction. If the transmitter and receiver are using an antenna like this and they are pointing towards each other, so we get the maximum gains here, well then we get 6 dBi here, 6 dBi here, that's 12 dBi, and in linear scale we have a factor 4 here, a factor 4 here, that becomes 16 times more signal energy pointing in the right direction. So we can improve the channel conditions by using directive antennas, but there is a price to pay. The effective area of the antenna needs to grow with the gain. So when we're looking at from a direction where the gain is large, it also needs to be physically large in that direction. The frequency spectrum that is used for wireless communication today are divided into 3 different categories. The low band, which is frequency up to 1 GHz, the mid band, which is the frequencies between 1 and 7 GHz, and the high band, which is above 7 GHz. And there are different types of wireless communication systems operating in these different bands. The low band is a traditional band for wireless communication, particularly over large distances. We have a rather limited bandwidth because if we are down at below 1 GHz, it's hard to find more than 10 or 20 MHz that can be utilized for one particular service. But the good thing is that we have a large wavelength. The lower the carrier frequency is, the larger is the wavelength, and therefore the signal propagation becomes better. The signal propagating better through different types of objects. In the high band, there is a lot of talk nowadays about millimeter wave bands, which are when we are above 28 GHz, because around that number we have a wavelength that is around 10 millimeters, and therefore we can measure it in millimeter. The good thing with these bands is that we can typically find a large amount of bandwidth, and we know that the capacity is improving with the bandwidth. We might even get 1 GHz of bandwidth in these bands. The bad thing is that we have a small wavelength, which means that the signal propagation is not so good when the signal needs to propagate through different obstacles. If we look at an isotropic antenna with the formulas from before, in the low band, an isotropic antenna have an effective area which is like 1 decimeter times 1 decimeter. In the mid band, it's like 3 centimeters times 3 centimeters, and in the high band, it's down at numbers measured in millimeters. This is interesting because in the low band, when something is of the size in decimeters, well, if we are putting up a fixed antenna somewhere, we can definitely use an isotropic antenna or something even larger with more directivity. However, we might not be able to squeeze that into a handset of a mobile phone. In the high band, the antennas are very small, so for that reason we can use directive antennas also in the handheld devices. We can use directive antennas in all these bands depending on what kind of device it is. So in the low band it might be used at a base station, which can be large enough to transmit towards users, and then the user have a isotropic antenna, while in the high band we can use it both at the transmitter, which might be a base station, and some kind of receiver. And this is what is used today for satellite communication, for example, in the millimeter wave bands. However, there is a problem when it comes to mobile communication, namely that having a directive antenna within the handset is not particularly useful, because you would like the handset to be able to be rotated in any way as you like, and to use it to move around. This also becomes problematic when you are putting directive antennas at base stations, while your users are allowed to move around, because if you have this type of a directive antenna here pointing towards the ground, then some users will be lucky and stand within the area where we are directing the signals from the transmitter. These users will have an advantage of having a directive antenna at the transmitter, even if themselves cannot have a directive antenna because of this possibility of being able to rotate your phone. However, some users might be located in other places where you still would like to provide coverage, and you couldn't know where the users are going to be in advance in mobile communications. So in this case, the signal needs to bounce off this building to make it behind this shadowing object, and in this case you see this directivity is not good. It's not pointing in the same direction as the blue arrows here. So this user will have a disadvantage of directivity, because what directivity really means is that you take energy and instead of spreading it out in all directions, you focus in some directions towards the lucky users, and the unlucky users get less energy with the directive antenna. So in order to provide good performance in mobile communication areas, we would like the directivity to be adaptive, so we can change it depending on where the user is. And we don't want the solution to be a mechanical one where when you're holding your phone, it rotates itself so that it's pointing in the right direction. No, we would like to find an electronic solution to this. So how can we create directivity? Well, here's an example of that. You have two antennas here, and they are sending out the same signal. And then they will propagate like this. So if you see this as a sinusoid, then if I'm writing a marker here as a circle every time we are at the upper part of the sinusoid, well, then we have waves that will propagate like this. The color here is representing signals that was transmitted at the same time. So the green signal was transmitted from both antennas at the same time, the orange one was also transmitted at the same time, and so on. There are some points here where the curves are intersecting. These are locations where the distance to the two transmitters is the same, and therefore the signals are received in phase at the same time, synchronized. And that happens in this direction here, and in that case we see what is known as constructive interference. So the received signal will look stronger than it would be with only one antenna. What happens now is that every antenna is transmitting signals uniformly in all directions, at least forward here. But when we are observing signals at different locations, it will be perceived as if we had a directivity in our transmission, because in this direction we will receive more because the signal components are in phase. We have the constructive interference. So when two antennas are transmitting exactly the same signal, it will look like the joint effect is a beam or directivity in this particular direction. Can we steer this directivity? Can we adapt it towards another location? What we can do is that we can delay the signals that are transmitted at the right antenna. So the green one here is transmitted at the same time as the brown here. And that means that there are other locations where the same signals will be received at the same time, namely in this direction. So now we are creating constructive interference in this angular direction. So with two antennas sending the same signals but with different delays, we can form a directivity in another direction. This is called beamforming. We are creating the directivity in a direction of interest, and this is called the beam. The traditional antennas that are used in mobile communications are actually strongly directive, but you need to make sure that they are directive in the elevation angle, so we are focusing the energy down to the ground and not up in the sky. But in the horizontal direction or azimuth directions, we would like to have little directivity so that we can serve users in different angle directions. Typically, an antenna like this is supposed to focus the signal at a 120-degree sector. But this is known as a passive antenna. It has a constant directivity. And now we are moving towards what is known as active antenna arrays or advanced antenna arrays, where we have multiple antennas. In this example, we have 64 antennas, each of them with just a weak amount of directivity. And they are shown here as 8x4, and then the cross here shows that these are so-called polarized antennas. So there are two antennas co-located but with different directivity in the polarization domain. And every antenna here have an integrated radio, so we can delay the signals in this way I was just describing. And that creates the possibility that the joint effect of this entire array is that we are focusing the signals strongly in different directions. And it's adaptive, so when the user is here, we can form a beam in that direction. When the user is here, we can form the beam in that direction, and so on. And the interesting thing is that we can do all of these things at the same time at the same frequency, because we are not mechanically rotating anything, we do this electronically. So we can send the yellow signal, blue signal, green signal, red signal at the same time by using different delays in these different antennas. And this type of 64 antenna arrays are very common in 5G nowadays, and they can do a lot of things that you can't do with a directive antenna. And in particular, in the rest of this lecture, I will mention three main benefits of multiple antenna communications. They are called the beamforming gain, spatial diversity, and spatial multiplexing. The goal of this lecture is to provide you with the conceptual idea and the historical perspective, and then we will cover the theory in later lectures. So the first benefit is adaptive beamforming, and this is what we already have talked about. So if you have one antenna that is transmitting omnidirectionally, then it doesn't matter where the receiver is, the signal energy will be focused in all directions equally much, or not focused in any direction at all. But if you have multiple antennas, say 6 antennas at this point here, and you are time delaying the signal so that you are focusing at this point, well then you are creating a signal beam like this. And the coloring here is showing how strong the signal are at different locations. Here they are spreading out as a circle, here they are spreading out, but you still have a directivity in this direction. So this is the beam. So the good thing is that you can direct your signal in any direction that you like, depending on where the user is. And of course, you need to know the direction in order to point the beam in that direction. The good thing with adaptive beamforming is that you can make use of directivity in any frequency band. So as you go up in frequency, the wavelengths get smaller, so therefore the isotropic antenna becomes smaller. It might only be a few millimeters large in the millimeter wave bands. And in those cases, either you live with an isotropic antenna that becomes very weak, or you increase the size of the antenna to get the directivity gain, but then it's fixed and it only works in fixed locations, not when the user is mobile. But if you're instead using an array of small antennas, well then you can use beamforming in order to steer directivity in the direction that you like, depending on how the user is located. The beamforming leads to a so-called beamforming gain, which is proportional to the number of antennas that you're having. So if you have m omnidirectional antennas, well then you will get an m times stronger signal at the location of the receiver, as compared to using just one antenna. And this is happening by only sending 1 mth of the power per antenna. So you're taking the same amount of power and spread it out over your antennas. Alternatively, if you would like to save energy, you can transmit with 1 mth of the power. And this is what is illustrated here. Actually, the value here that you are getting at the location of the receiver is the same in both cases. But in the lower case here with the directivity, I'm only using 1/6 of the power, but I'm still delivering the same signal energy here, because I'm taking away energy from all other directions. The idea of using beamforming has been around for a long time, so you can even find a paper from 1919 by Alexanderson called Transatlantic Radio Communication, which is talking about large antennas they were putting out in New Jersey in order to communicate over the Atlantic. And these antennas were used during the First World War in order to communicate between America and Europe. They were using this kind of constructive, destructive interference patterns, and they were saving a lot of energy while extending the range over the Atlantic. We are delivering a beamforming gain by having multiple antennas that you are sending the same signals from, so that you are creating constructive interference over the air in the direction that you like. Another benefit appears when you have multiple propagation paths. So say that you have a transmitter that is sending a sinusoid, sine 2 pi t. Then you have an additional propagation path where the signal is supposed to bounce off this object here. And this path is longer, so for that reason the signal that we are receiving over this reflected path have an additional phase shift. So the received signal is a summation over these two. And by using some trigonometric rules, we can rewrite this summation over two sines with different angles as 2 times the cosine of this phase shift theta divided by 2 times the original signal sine 2 pi t. And here we have a phase shift as well, so it's sort of the average between the two different phases. So this is a sinusoid that's varying over time, and this is the amplitude that it's having. And it depends on what value theta is having here. So if theta is equal to 0, well then these two paths are in line with each other, and we get twice the amplitude. And if theta is equal to pi, then these two signs are having the opposite sign, they're cancelling out each other, and cos of pi over 2 becomes 0. So the amplitude can be anything between 0 and 2 depending on if you get constructive or destructive interference between these two different sine waves. As the transmitter or receiver is moving around, well then this phase shift will vary and we will have variations in the amplitude, and that creates what is known as fading. The channel is sometimes good, sometimes bad, and it's the randomness created by this propagation environment that is creating those type of effects. And this is something that has been known for a long time in wireless communication, and also people have been talking about different methods in order to mitigate it for a long time. You can find something called spatial diversity all the way back in a paper called Linear Diversity Combining Techniques from 1959. In this work, the idea was to protect the communication against both channel fading and noise by having multiple antennas that are observing the transmitted signal. These antennas should see different independent observation of the channels. You can view it as different random theta values from the previous page. And in that case, you should have a small risk that multiple observations are all bad at the same time, which is providing you with the reliability. And this is called diversity gain. There are many types of diversity. You can have a diversity in time by sending the same signal multiple times. You can have a diversity in frequency because the channel might vary over the frequency domain, but this is focused on diversity in the spatial domain by having multiple antennas observing independent realizations of a random channel. So far I have focused on communication between one transmitter and one receiver, but when you put this together in a network, we have many users that would like to communicate with base station or with each other, well then you need to have an infrastructure for that. Already in the 1950s, Bell Labs were looking into how you could build a network for mobile telephony where many users can share the resources. And the idea was that at every given location, only one user can use every frequency. But you would like to reuse these frequencies over space. So that's why you create a cellular network with different fixed base stations that are covering different regions. And then the users within one region should connect to that base station, and you can reuse your spectrum in different cells, either in every cell, or you can have a fractional spectrum reuse where every third cell, for example, is using the same spectrum, and in that way you're controlling the interference. And one can also use power control by telling that devices that are close to base stations should cut down on their power so they're not interfering too much with their neighborhoods. The first cellular networks were deployed in the 70s, and then the 80s and 90s and so on. The use of them have increased more and more, and that had led to a traffic growth. Originally, these networks were used for mobile telephony, but nowadays they're used mainly for mobile data traffic. And if you look at North America, Here we can see numbers from the Ericsson Mobility Report in exabyte per month of the data traffic in North America and how it varies with the year. And we can see that there is an exponential growth. The data traffic is increasing by 30% every year. And that means that we need to improve the wireless technology all the time in order to cater for this. And this has been achieved by adding more base station, so the regions of the cells become smaller. We have been using more frequency spectrum, and now the question is, can we use multiple antennas to continue sustaining this trend as well? Sort of using the same base station location but more advanced hardware on the base station. Well, this is precisely what 5G is trying to do. And the idea is something called Space Division Multiple Access, or SDMA, where we have multiple users that are communicating at the same time. This is a paper from 1990 that is illustrating this. We have a base station that is sending beams towards different vehicles, because at that time mobile phones were typically car phones. And what this is illustrating is that we can serve multiple users at the same time. This is called spatial multiplexing. So many users can use the same frequencies at the same time as long as they are located in different angular directions like this, by sending different beams. And you can do this also in cases where we have more complicated propagation environment, so we don't form angular beams, and we will look at that later in the course. So with this technology, every base station can handle more users, and that's why it's utilized in 4G and 5G and Wi-Fi 5 and 6. The performance gain is called the multiplexing gain. Essentially, the capacity per user stays the same, but you can get many more users being active at the same time in the same area, and therefore the capacity is multiplied with what is called the multiplexing gain. This technology was called Space Division Multiple Access when it was invented. Nowadays it's called multi-user MIMO. Around the same time, the idea of something called point-to-point multiple input, multiple output, or MIMO appeared. This is based on the idea of sending multiple beams to the same receiver, and this was actually an idea that showed up later than serving different users. Precisely for the reason that from the beginning we were after trying to multiplex as many mobile phone calls as possible, and using mobile technology in order to deliver higher data rates is something that come later. But here we can send multiple streams to the same user, and then we need to have a propagation environment where beams sent in different directions will lead to the receiver. So it might be bouncing off different objects, and you might have a direct path. And this is also supported in 4G and 5G and Wi-Fi 5 and 6, and this is also called the multiplexing gain. Finally, what is the outline of this course that we will consider? Well, in this lecture I talked about the motivation for having multiple antennas, and the history of multiple antenna communications, and the 3 different benefits that you can have from that. In the next lecture, I will talk about the basic of multi-antenna channels, and then we will go on and talk about diversity and ergodic capacity. This is a concept that appears when we have random channels. Then we will look at the point-to-point MIMO channel in more detail, and then the rest of the course will focus on the multi-user MIMO scenarios, talking about things like capacity bounds, channel estimation, power control, and go into all of the nice details on how to do this in practice. The first part of the course is covered by a manuscript called Introduction to Multiple Antenna Communications, and the rest is based on the book Fundamentals of Massive MIMO. And there is some overlap when it comes to the beginning of multi-user MIMO between these 2 different texts. Mobile communication systems can be improved a lot by having multiple antennas at the transmitter and at the receiver. We can use it for beamforming, where we are directing a signal from transmitter towards the receiver, and we are listening in a directive manner from the receiver side. This is like having directive antennas, but it's adaptive, so we always can get this gain irrespective of how we're rotating the devices. We can also combat fading, so the randomness in the channels, by having a diversity. We are observing different random realization of the channels at different antennas. Finally, we can also get a multiplexing gain where we can transmit directive transmissions to multiple users at the same time, or we can send multiple streams to the same user. And this is something we can do both in the low band, in the mid band, and the high band.